be listening. Okay. Anyways, so we got a nice little graphic here. Anyways, so we're entering into the last legs of the course. This is the second to last lecture of course content, so to speak. What I mean by that is that this lecture and then Thursday's lecture, imperative programming, are going to be the last scheduled 150 things. After that, I get to have 3 lectures of fun because I'm going to give you 2 lectures on special topics. I'll teach compilers and program analysis, and I highly recommend you come to those because it's going to be fun, and I'm going to be teaching things you wouldn't be able to learn at this level anywhere else, really. Okay. And also the final lecture, which I'm mandating all of you go to. The lazy programming will be what we're doing today. So let's go ahead and get started. Oh, that's not a happy sound. What is this? There we go. Okay, we're going to be talking about a few things today, but we got lazy evaluation. We're going to be looking at a structure for doing such. And we're going to talk about this thing called infinite data structures, which is kind of a flashy term, but it's actually really, really cool. And it will kind of open up the kind of array of things that we are allowed to do in SML and in functional languages in general. And then some addendums on like what we'll actually test you on is maximal laziness and streams. And if we have time, we'll get to primes, okay, which I think are really cool. So firstly, lazy evaluation. Well, I've got a question for you here, all right? You know, we've been programming in ML for kind of a long time now. I'm going to define a function for you. We're going to do a little, what does this code do? Okay, I'm going to define a first function for you. This is the function that gets the first projection, the first component of a tuple. And I'm going to ask you this. What is the behavior of first given 1 and 1 div 0? What's this do? That's funny. That's not necessarily true. Yeah. It raises div. Absolutely. Why? Why does it raise div? Because eager evaluation. But like, isn't that kind of silly? I asked for the first projection of this tuple, and this tuple has 1 in it. I know it's 1. Why can't I get 1? Well, this is how SML plays the rules, but it's not the only way to play the rules. Okay. So you're absolutely right that by eager evaluation, so eager evaluation is going to imply that we get raised div, right? But we're not always going to be able to have that behavior depending on how we decide to structure things, okay? So this would only happen if the second component looped forever or raised an exception. If we didn't do that, we would be able to do this properly. But either way, like even if those 2 cases happen, we want to make sure that this first function works. And we can imagine that also if we were to have not just something that looped forever or raised an exception, like some really, really long computation, I don't really care enough to wait for this computation if I'm going to immediately throw it away with the first function, right? I don't care enough. So let's try to be lazy about it. Let's try to do less work. So the way that this works is, by analogy also is, suppose I do map f of L, and the list L is like 9,000 elements long, and then I cons off the first 2. I only wanted the first 2 elements, but what map FL is going to do is because it's eager, it's going to go and fully commit and apply F to every single element in the list. Now that's kind of silly, right? So again, this whole idea of by the rules of eager evaluation, by doing things kind of as we can, we're wasting work. We're wasting cycles of our computers, okay? And that's kind of bad. So let's try to be lazy about it. Lazy evaluation is a kind of evaluation scheme that's completely opposite to that of eager evaluation. In lazy evaluation, we only compute expressions. We reduce them to values only when their value is needed. So in this example I have here, for instance, in a lazy language, we would get 1, okay? And the general theme about lazy languages is if I have anything like val x equals e, no matter what e is, this runs in constant time in a lazy language. Why? Because what's going to happen is, what normally happens, right, is we say, oh man, e goes to some value v, right? Remember our notation from forever ago. E goes to some value v, and then I produce an environment where I have v bound for x, right? And then I march on my merry way. In a lazy language, and this is the eager case. So in the eager case, this is what happens. In the lazy case, I just say, let me bind e to x. I don't simplify it whatsoever. This E might be a super ginormously large expression, like a giant concatenation of strings or addition of numbers. I might be able I should be able to apply it, but I won't. So in a lazy language, we can also do something like this. Suppose I had this list 999, 998, 997, 996, 995. And I fold over it where I take the previous thing and I multiply it by the next thing, and then I compute factor that twice. I do a double fact. All right. You can imagine this number might get slightly large on us. But in a lazy language, this is O of 1. This runs instantly. Because what do? I bind res to this computation, exactly this expression. But in an eager evaluation case, this would take between ludicrously long and forever. And in fact, what would likely happen is it would raise overflow in your machine. Okay. But let's set that aside for a second, because that we usually pretend that doesn't happen. So we're going to get some benefits here in that we only want to be able to have this happen if we need that value to be computed. Okay, and for instance, something that might warrant needing a value is, suppose I do something like this. Case x of 1 goes to E1 and then otherwise goes to E2, right? In an eager language, if I have x that is a value, then like x is a variable, right? Which means it must have a value. This is very fast. I just compare. In a lazy language, this is going to express the intent to what I'm going to say force. We force the value here. So here we have no choice, but we take the the e for x, that's the e that's bound to x, and we evaluate e to a value, and then we dispatch on what that value is. But only once we get to like actually scrutinizing the contents of that variable do we actually compute this expression. Okay, I think this is going to be similar here, where I'm yeah. So basically the key conceptual difference here is variables are bound to expressions in a lazy language versus variables being bound to values in SML. Does that make sense? Like in SML, we always only ever produce a binding if it's to a value. In a lazy language, we can bind to an expression always. Okay, so there's a distinction between the cases of when I do val x equals e, this could loop forever or raise an exception on me, or just take a really long time. But in a lazy language, all of these cases are conflated. Okay, I realize I keep saying in a lazy language, and we haven't worked in a lazy language, so maybe it's hard to get the intuition. But we're going to find that actually we can do a kind of lazy thing still in SML. Okay, yeah. Oh, I had something similar. Okay, cool. All right. So laziness in concept, it seems okay. It seems all right, right? Pay for what you need, right? Only pay the computations that you actually want to use, which is great. I don't want to waste cycles. Nobody wants to waste cycles, right? We could be doing other things with this compute time. We could be training ChatGPT 4.5, right? But instead of this, what we should actually be doing is we should be a little more careful about laziness, because it has some benefits, but it also has some detriments to it. So the main detriment here being something I've harped on about before, but predictability. Okay, as a programmer, as a software engineer, as somebody who works with computers, okay, you want predictable behavior. If I open up Microsoft Word today and it's in teal, okay, and then the start bar is on the right hand side, I'm gonna be sad about that. Okay, I don't use Microsoft Word, but if I did, I'd be upset about it. The point is that when you're writing software, you want predictable behavior from your language, and when you're running software, you want predictable behavior. So let me give you an example. Let me set the stage. Suppose that you're in a lazy programming language, like SML but lazy, and you have an API that returns an int list to some user. Okay, you've implemented some library that returns an int list. All right, and then somebody reads your documentation online, and they find your open source code, and they're like, "That's exactly what I need. I need that int list." So they pull your code onto their computer and they run it, and then they run your function and they take the result and they bind it to a variable, right, in some lazy language. And then they go and they do their thing, and they're like, "Thanks. All right, now I'm going to go do my thing and forget you existed." Well, 120 production hours later, their web server crashes because of an unexpected error. And you know what happened? You handed them this list. You handed them raise div, raise div, raise div. Okay? This can happen in a lazy language. I can say I'm giving you an int list, and I can hand you nonsense and you won't know. You won't know until you force these values. So suppose they were pulling out like some kind of API to I don't know, like some bank balance. I don't know what the ints actually are. But the point is that they passed it around to the web server and they didn't touch it and they didn't look at it for like 120 hours. And then eventually somebody clicked a button. They said, let me look at my transaction value, and then raised it. All right. Terrible. Absolutely awful. So it might seem ridiculous, but in a lazy language, every exchange of data, every time I give you data, I'm not giving you data as in like values. I'm giving you completely arbitrary computation. I'm giving you anything that fits into a variable, which is anything at all. Very, very dangerous, very, very unsafe, right? So in an eager language, if I'm able to get an output and I'm able to bind it, I know it's a value. I know it's safe. I know it'll never do anything bad to me. Okay, I can trust that variable. All right, it's my best friend. But for this poor consumer, they got 3 ticking time bombs, and that's what they were: raise div, raise div, raise div. Time bombs that would go off eventually once they were actually looked at by whatever code. Okay, and they didn't have the opportunity to handle it. They didn't know it was going to be raise div. And this is actually probably a totally believable mistake. Like suppose that this was like computing some kind of average, and then it divided by what? The number of things, and then the number of things was 0 by accident. Raised it, right? Perfectly believable explanation. But that, your consumer's not going to be happy with your perfectly believable explanation of why you should hand them a time bomb. Okay, so don't hand people time bombs. Let's do better. All right. So it doesn't need to be necessarily even raised div, because what would happen is, more realistically, right? In a lazy language, I go and I hand you some list. I hand you x1 through xn. Okay, and that's fine. But each of these x1 through xn's might be a lengthy computation. Suppose I'm computing, like scraping through a database to find your searches or whatever. Then forcing this becomes very, very unintuitive in terms of how long does this take? If I do a case, if I ever case on some kind of variable, is it going to take instantaneously if it's already a value? Or is it going to take like 2 seconds? Might not seem like much, but are you going to, if there's a great study I read once about how browser traffic relates to how fast the page loads. It's actually really insightful. And basically the idea is simply that it matters a lot how responsive a website is for how many people use it. And some people claim, I think that there's some popular website out there that its popularity can be attributed in part to the fact that it highly prioritizes reactivity and consumer friendliness. This is the same idea. If I go to click your button and it takes 2 seconds before I can go there, you're done. You're not making it on the free market. Okay, it's capitalism's going to eat you alive. All right, you're out. So let's not do that. All right, doesn't need to be raised if it could be anything. That's the point. Okay, so ultimately in a lazy language, the idea is just that things like map f are constant time, and only when you force it do you get linear cost, and that makes it really difficult to give any sort of rigorous treatment to asymptotic analysis. Because then what do I do in a lazy language? Every single one of your workspan questions this semester, almost always, is O of 1. You're done, right? It's constant time. And then you ask, what about later? And you're like, oh yeah, you didn't ask me about later. Right now it's O of 1. I remember hearing about someone who had a interview, and in their interview, they were asked to reverse an array in O of 1. Okay? And it sounds impossible, but like what they did is they just returned to the same array, and then they had like an updated access function that just like does the n minus thing. So like laziness is kind of interesting in the sense that you can just do no work, and as long as you set yourself up to do the requisite work later. So it is possible to reverse a list in O of 1. Yeah. Literally don't worry about it. See me after class. This is purely a technical detail I'm obliged to put because I've heard this for years, but it does not matter in the context of this class. Okay. Okay, I gave you a lot of negatives for lazy evaluation, but SML is an eager language anyways, right? So why am I kicking the horse? Why am I punching the bag? Well, we can actually still do lazy stuff insofar as it serves us, right? Lazy evaluation can be a cruel mistress, because what happens is when you implement laziness, or when you're working in a lazy language, you have no choice. Everything is lazy all the time, okay? Be lazy some of the time. We can take advantage of this for ourselves and take a few lessons from lazy evaluation when we're dealing with just regular SML, okay? So here's a question then. Based on that, like, what does it sound like when I say binding a computation to a variable instead of binding some kind of value? What does that kind of make you think of? I can't hear you. Okay, cool. Yeah, thank you. I actually could not hear you. Indeed, it should sound like a function. So suppose that in a lazy language we have this, right? Val res equals map FL. And what will happen is this won't be evaluated. We'll just bind the computation of it to res. In an eager language, we're just going to do this. Doesn't need to be unit, but the point is that we put it in a lambda. We put it in a suspension. This thing, remember, lambdas do not evaluate their arguments or their bodies until they get an argument. Doesn't matter if the argument is stupid, and they totally could evaluate this if they wanted to. They don't, which means that this is equivalent to doing that in a lazy language, in an eager language. This is the eager language, to be clear. Okay, but by analogy, we can do this kind of thing where we don't do the computation. Okay. All right. So the point here being, and you know, in a different class, I might harp on more about this, but eager languages can simulate laziness using these lambdas, and that's exactly what we're going to do today. This is called a thunk. It's a technical term. I'm so serious about that. A thunk is a value of type unit to t for some type t. We can also call it a suspension. It's called a thunk. You can go back in the literature. I don't know why it's called that. But the point is that for any expression e, I can turn it into a thunk by encasing it inside of an fn unit goes to, and then now it's suspended. Now it doesn't do anything until I go and actually evaluate it, right? Okay, so the key fact here is just that lambdas will suspend the contents of their bodies, all right? Always, always, always. If there's 1 + 1 inside of a lambda, it doesn't happen, okay, until you get the argument. Okay, sure. And I'll say again, like the point of laziness is that we can do it when we want to. So we're going to see select cases where it's useful to be lazy in SML, but the things about, like, you know, having an API and me handing you 3 ticking time bombs, like that will not be a problem in SML, okay? That will not be a problem in what we're doing. And this is a general concept of, if you have a language feature, generally it's better to be opt-in than opt-always, okay? We saw this with mutability in a sense. What we're going to do, next lecture, we're going to see that mutability is only a daemon if it's on all the time, okay? Opt into language features that are contentious, don't have them on by default. And this is a general kind of like API design thing, probably, I guess. I don't know, I never took a class in API design. All right. So that's going to be our policy. Simulate laziness, don't opt in all the time, okay? All right, that'll give us the benefits without any of the detriments. Any questions on this section? Yeah. Yes, but like limitedly. Like yes, but in like a hacky, like stupid way. Right? Haskell has some certain, Haskell is the premier example of a purely functional, very lazy language, and it has certain things that let you force expressions. But the fact that you always by default have these things around means that it's just not good for you at all. Yeah, and I think there's also some technical problems with that. There's a blog post about that. I can link it. Yeah, good question. Okay, anything else? No, I'm running low on high choose, so the answer is no. Okay, let's do a lazy structure. So, laziness is so powerful that we're going to have our own module and our own type for laziness, so that we can be very, very clear about when something is a lazy value. All right. Here is our signature. All right. The signature for lazy is going to be containing some type alpha t, and alpha t is like, and the way you should always think about alpha t is it's some manner of box, that has something to do with alpha. And the point of this box is that a lazy box is one where the box contains alpha, but only once you force it, okay? It contains a suspension of type alpha. And what I mean by that is we're going to have a function lazy that takes in a literal thunk that returns alpha, and then it promotes it into a lazy value, okay? And then force is going to take in a lazy value and then give us back out the lazy value that, or it's going to take a lazy value and give us the value that that computation evaluates to. Okay, and we can implement it like so. So if I wanted to implement this structure, I would call it lazy, and I would ascribe opaquely to lazy in caps. It's a little confusing that these things read the same. Not sig, substruct, end. Okay, so note that I've left the type of alpha t abstract. It's because to a user, they shouldn't have to think about what the heck this type even really is, okay? It could be anything, right? But the point is that it encodes a suspend computation. You know, like we could do a lot of work, or I could just say this. It's just going to have the same type. It's going to have the same type on the inside. But now, to someone using the structure, like they don't know, they get to maintain that conceptual divide between something of lazy type and not. And that means that fun lazy is simply going to take in a unit to alpha and return alpha t, which is also a unit to alpha. So it'll be the identity function. And then my forcing function, which takes in a alpha t, which is a unit to alpha function, right? Takes in f, and then it just calls f on unit. And then I'm done. Anything contentious about this? Everyone clear on this? This is a very, yeah. Yes, indeed. If we wanted to have this be alpha to alpha t, this would no longer work, because what happen is that we'd say lazy, like loop forever, and then we'd loop forever before we entered lazy. So yes, in an eager language, we do need to create the thunk first. The thunk has to be static. Yeah, okay, that's a good observation. Yeah, so one thing I'll note about that also is, well, okay, huh? You don't get a vote. So, okay. All right, okay. What is this? What is this, Haichu communism? You're just passing all around, distributing? Okay, all right. We got 2 left to do that too, so make it a good one, I guess. Okay, so what was I saying? Oh my God. Oh yeah, in certain extensions of standard ML, there you can do this kind of thing where you do give it like a keyword lazy E, and then it does create the thunk for you automatically, but that doesn't happen, so forget I told you that. Don't do that on your homework, you'll mess up. But just saying that, like, that can be a syntax extension, right? Most things can be syntax extensions. Okay. All right. So that's how we're going to use this lazy structure. All right. And we can use this because what happens is that eventually I get to pass around values that have type alpha lazy dot t. And that's pretty darn indicative. This says I'm holding a lazy value. So again, this type level distinction is also a useful conceptual distinction in your brain on what the heck this thing really is. Okay. All right. Okay. And then I showed you the implementation, blah, 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 blah. All right. So if I, for instance, gave you this code where I said tabulate a list of length 100 such that each entry is going to be lazy applied to a thunk that computes the, ith square number. Now I'm not holding a list of the 1 through 100 square numbers. I'm now holding a list of lazy values, of suspensions of those square numbers. It means that this will, first of all, in an eager language, okay, we're not talking about the lazy language anymore. This is eager. This also runs in it runs on O of n, but it runs in not needing to compute this. Or rather, it computes this, but it doesn't compute this. Okay, the language gets confusing for this. They are suspensions of each square number that can be forced later, right? And this is contrived because this costs almost nothing, right? But you can imagine putting some really friggin' expensive operations behind each of these suspensions. At work, this is something we do because one such use case for you doing this is not having to do I/O, not having to read from a file or make a network call unless you have to. Okay, so this kind of thing, like if you're eventually going to do it, but you don't need to do it now, maybe it's better to wait dynamically and see if you really need the suspended value. So the point is that depending on what the code does after this, we might see whether we actually compute the ith square number, but that's on a case-by-case basis. I don't need to, so I might as well not. All right. So this can be very useful, even though this example is contrived, is what I'm trying to say. And then finally, in languages like Haskell, we also memoize these lazy values. So that means that we only compute it once. And once we've computed it once, we remember always what that result was. This does not do that. There's no memoization here. As in, if I force the same lazy value twice, it will take the same amount of time approximately. And I will have, and if forcing it once takes 3 years, forcing it twice will take 6 years. Okay. It doesn't need to, but it will. All right. So that's something to note as well. We could implement this in a memoized way, and I believe there's actually a review lab problem on this called Haskell. I don't know if we're running it, but it exists, and I kind of like it. Okay. Quiz time. All right. They put yourself in the lazy mindset. Okay. You might as well not have taken the quiz until we force the grades, right? Okay. Part 3. Something very flashy I got for you. Infinite data structures. All right. Infinite power. ADB living space. All right. So we're going to be talking about data structures that can be potentially infinite. And I'm going to put this little scenario into your brains and we're going to think about it for a second. But suppose the CEO of your company walks in the room and she says she wants all the integers. And you pause for a second and you're like, I don't know about this, boss. I don't know if you know, but the integers are infinite. And then she says, yes, actually, I'm very perfectly aware of that. Are you talking back to me? And you say, okay, yes, I will have the integers on your desk by next Tuesday. All right. Realistic corporate example, by the way. Don't backtalk, right? She knows yeah. Anyways, well, this is not dissimilar than the following image, okay? Mom, can I have all the integers? No, there is all the integers at home. But all the integers at home is this code, where I say integers n is n cons negative n cons integers n plus 1. And then I run this on 1 and I cons 0 to that. I don't know if you know this, but this code loops forever, okay? Does anyone need justification as to why this code loops forever? Yeah. Can I trace it through? It's going to be an infinitely long trace, so no. No. Well, yes, but okay. The point is, actually, to be fair, I've actually never tried the negative operator, so it's possible there's a bug there. But anyways, this takes an infinitely long time to evaluate. This will never terminate, because guess what? The integers are infinite. I can't hand you a list containing all the integers, okay? So all the integers, this is not it, okay? We need to think of something better. So we're going to be able to write a function that's very similar to this, actually, but we will actually be able to hold all the integers, okay? And then you will be able to appease your CEO who wants all the integers, okay? Here's the issue. We need to make sure this doesn't loop forever. So let's contain the looping forever. Let's use laziness, all right? We can nicely define the integers, but the fact that we can't do it because we don't have infinite amounts of space, like that's kind of a lame excuse, okay? If anyone ever says physical constraints as a reason why you can't do anything, that's a lame excuse, okay? So I remember I took a class on quantum computation, and on the very first day, the professor comes in and he says, all right, this has nothing to do with engineering, nothing to do with like physically how this is possible. Assume you have things called measuring devices, which are the key of quantum computation. And then we assumed that they existed. And then we did that for 15 weeks, okay? Same thing here, all right? Except better. So physical constraints, kind of lame. We also know that it's impossible to have infinitely many processors though, right? And that didn't stop us. So let's not let this stop us now, all right? Physical impossibility is secondary to our concerns. Infinite data structures are a kind of data structure that can store infinitely many entries, and they don't need to loop forever to do it, okay? But they can store, they can quotation marks store. And the reason why this works is because we're going to play around with the idea of what store means. Memory concern is legit. We can't use a list, but what we'll use is we're going to use something called a lazy list, which is a list that can be infinite, can have infinitely many entries, okay? It's sort of like this, right? If you told me you wanted all of the natural numbers, it is perfectly fine for me to say, yeah, I'll give you all the natural numbers. You can have 0, and you can also have successor of any natural number. I have given you every single natural number. Okay, that's a perfectly fine way to. It's a dissatisfying way to do it, but you didn't say to do it in a satisfying way. You told me that you wanted all the natural numbers. So it's like kind of the point of laziness is kind of like malicious compliance in a sense. Okay, here's the idea. I can define for you this data type, which is real SML code for once, and this data type alpha list prime will be the nil constructor or the cons constructor of alpha and an alpha list prime, okay? So you should be able to convince yourself this is pretty much exactly equivalent to the real lists, okay? But I'm showing you that we can do this so I can draw an analogy, okay? So this is almost exactly equivalent to alpha list. Well, it is exactly equivalent. But here's how we're going to define lazy lists. Instead of storing a value, or rather like storing the list value of the rest of the lazy list, we are going to store a suspension of a lazy list. What this practically means is that a lazy list can not necessarily have to come up with the rest of the list. It only has to have the ideas of how to make the rest of the list. This is kind of like the 0 and successor of 0 of any natural number idea, okay? And with this data type, we are going to be able to encode infinite data structures, okay? Okay, so what does this mean? If I want to make an alpha L list, I don't have to come up with exactly the lazy list. I just have to come up with the lambda or any kind of function. A recursive function would suffice as well. So sort of by analogy to what I was saying in CPS lecture, we have a list that has instructions that tell us how to make the rest of the lazy list. And that is itself a perfectly fine list. So here's some examples of values of type T list, L list. Actually, I think all these are of type int list. Oh, this one's actually alpha. Nil is going to be of type alpha L list. Makes sense, right? If you remember polymorphism, that's how it works. Cons of 1 comma a thunk of nil, right? It needs to be a thunk of nil or it won't type check. Has type int L list. Cons of 1 comma a thunk, where this thunk itself is cons of 2 comma a thunk of nil, is also of type int L list, right? It looks the same as like a list, but now instead of being able to just cons onto something directly, I have to take the suspension first. Okay. But also this one, I don't need to have the cons there. In fact, I don't need to give you anything at all. This is an this is an int L list that has 1 on it. Okay. And then when you ask for the next element, it's going to loop on you forever. That's the price of laziness. Yeah. Thank you. Actually, I think it's less readable that way. But yes. So we can just do this. But you put me off my rhythm. You expose it and it loops forever. That's the price of laziness. Whenever you expose a lazy structure, you might get anything. You might get an infinite loop. You might get a really long time, and you might get a raising exception. Okay. And it might also come up to you with cons again, or nil, or whatever. Okay. But the point is that this thing here can be like a recursive function call, or a recursive function. And that's where we get into the really interesting territory. Okay. Yes. Okay. All right. So now instead of writing down something in a finite amount of space, what we're going to do is we're going to use a recursive function to encode the instructions of the rest of the list. So here's how I would write the natural numbers as a lazy list. I say nats from, so I need a place to start. I have an accumulator, which is the nat I'm currently on. Okay. And then I say, okay, this lazy list must be cons, where I have n, my current thing, and then a suspension that generates every natural number from n plus 1 on, right? And that should intuitively make sense to you. If I want to give you all of the natural numbers greater than n, I give you n, and I give you the rest of the natural numbers greater than n. It sounds dissatisfying, but in code, like this is a perfectly fine way to do it. And then if I want to get all of the natural numbers, I'd say start at 0. Note that like one thing about this function here is that it doesn't have a base case. It doesn't need one. Most I would say, yeah, most stream functions, most lazy list functions don't need a base case. You can just do it like this. Okay. So we're not looping forever. We're just petering out we're segmenting our evaluation. If we wanted to go and compute all of the natural numbers, yes, it would loop forever. But what we do is we chop them up into discrete bite-sized time periods and then separate them by each n. And that is fine in practice. Yeah. If you wanted to have a lazy list, you might want to be able, well, exactly, okay. So one reason, so you can reverse a list in O of 1 and pass the job interview, okay? The second reason for this, and the second reason for this being that having lazy data structures is sometimes useful because you don't want to actually pay upfront the cost of what you're doing. Laziness can help you if you're trying to save on like performance and you don't really care about it, and you're aware, you are careful about the detriments I told you about previously. But there's no reason why like this is any less useful to you than having the list in a real form, so to speak. Oh, those are two very different. Yeah. It's kind of funny how those are. Okay. How do you extract a value from this? Yeah, so let's get into that. Well, what's going to happen is that you can pattern match on an alpha L list, right? An alpha L list has the same structure where you say it's going to be nil, or it's cons of an element and then the rest of the tail of the L list. So to extract a value from a lazy list, you just pattern match on it. You have nil, in which case you have nothing, or you have cons, in which case you have the first thing, and then if you wanted to get more, you could optionally force the rest of the L list. Okay, so it doesn't look super different. It's just that when you pattern match, you're not guaranteed to get the rest of the L list. You have to go and compute it for yourself, however many. Okay, there's a cool function take where you like can convert an L list into a list by saying I want to take the first n elements. I haven't put it on the slides for you here, but I highly suggest that you try to implement it yourself. I think it's a good exercise. Okay, and probably you'll do it on like the lab or the homework or whatever. But it's a good exercise. Okay. All right. Extract value. Jesus. Okay. Suppose I wanted to construct a lazy list from an arbitrary function. That is, I wanted to tabulate in the same way as I have my list.tabulate, and I'm sure what all of you are familiar with by now, your sequence.tabulate. Okay. Lazy tabulate is going to take in an int to alpha function and give me back an alpha L list. And in fact, what it's going to do is what's kind of interesting is I don't need an n, right? I don't need to say of length n. It'll just do whatever that function is defined to be. Maybe it raises an exception. Maybe eventually it says that loops forever, but lazy tabulate doesn't need an index, okay? It doesn't need a limit. Okay, and here's how I would define it. Oh, whoops, I should write this on the board. Sorry, my bad. Okay, let's do it. So let's do lazy tabulate. And what I'm going to take in is I'm going to take in a function f, and now I need to come up with a list, right? So what I'm going to do is, well, I also need to have some kind of like index, right? I need to know where I am. So we're going to do this recursively and by storing an index. Okay, we're going to say that we're going to tabulate from I onwards. Okay, this is kind of a recurring theme with lazy lists. We store this kind of like onwards thing. And then what do I say? I say cons. Actually, let me do it in this line. I'm going to say that I'm going to have cons where I take the thing I'm currently at, which is f of I, and then I return a suspension of lazy tabulate prime, right? My helper again, where I give it f and I give it I plus 1. And then if I wanted to define lazy tabulate, I would, I'll just do it. No, I can't do it that way. Sad. I could partially apply it, but I can't actually. So lazy tabulate of f is just going to be lazy tabulate, which is a really long function name, I realize now. Prime given f given 0. Okay? Does that make sense to everyone? Yeah. Yes, it does. It does indeed. Very good observation. We're going to get to that in like 3 slides here. That's precisely what it does. Next thing I wanted to talk about. I'll get to it. We'll see why that is. All right. So this is going to be the function, and I'll get to what he just said in a second. But do people trust me that this is like lazy tabulate from 0 onwards? Right. I just straightforwardly do it. I don't have a base case because I get to run wild in here. I like to call this place Thunkland. When you're in a thunk, you're in Thunkland, and in Thunkland, nothing happens. Okay, but things could happen. All right. It's like a job offer. Like everything could happen, but in practice, nothing happens. Okay. Sometimes. All right. So if we try it on a specific use case, what I could do is I could make a lazy list such that I get, I don't know, for some reason, 1024 divided by every single natural number ever. By every single natural number ever, right? I could do that, but what do you think is going to happen based on what he has said? Raise div. It purportedly contains all of the results of dividing 1024 by every natural number, but it doesn't, because the first natural number, and fight me on this if you don't think this is the case, is 0, which means if I divide by 0, I'm going to get raised div. So we're not going to have anything. And that is not lazy enough. Okay, this is like pretty lazy. It's like marginally lazy. Like it's not to the point of laziness that I like it to be though, right? Because all I said was I wanted to be able to have a lazy list that every entry was 1024 divided by I. But I never said I wanted to look at each element. There's a difference there, okay? So what we're going to find with lazy lists is that they're not lazy enough because we have no choice. If you go and look back at the definition, which is way too far now, but we have nil or we have cons of, you know, alpha star whatever, okay? But the point here is that if I have cons, I must be holding the first element, even though my value must be holding the first element, even though I never necessarily said I want to look at the first element. Okay, these are two different things. Having to hold it versus expressing the intent to look at it. Those are not necessarily always go together. Okay, so we're going to try and come up with something where we don't need to have this problem. We're going to have an improvement on lazy lists called streams, and the point of streams is that a stream doesn't have this issue. A stream is like a maximally lazy data structure, let's say. Okay, in that I only ever have to compute something if I expressly say yes, I want it. Okay, is this concrete enough of an example for everyone? Does everyone get what I'm saying here? Okay, speak now or don't. All right. Maximal laziness and streams. So the definition of maximal laziness is one that definitely doesn't compute any element until it's absolutely needed. Maximal laziness will mean something slightly different on your homework, but in intention, in intuition, this is what you should have it mean? Okay, it means we don't do any work until we absolutely have to. The first element, we should have to express the intent to look at it before we force it. Okay, and this is going to be our type. Let me write it out on the board just so that you have this for posterity. But it's going to be two types actually. And the cool thing about this type is that it is mutually recursive, which is an idea that I've alluded to, and I'm pretty sure I showed you a mutually recursive function at some point. But it's going to be this. So we have a stream. A stream is just something where it is a lazy list essentially. But a stream, you need to explicitly say, yes, I want the first element before it gives it to you. So that means that a stream is going to be a suspension. It's going to be a thunk of something called an alpha front. And what is an alpha front? Well, let me tell you. I use and, this keyword here, because I'm defining a mutually recursive type. Both these types will see each other. And I have that an alpha front is going to be the same thing we said earlier, nil or cons of alpha star, but now the tail of a front is another stream. Now this might look very, very similar, okay? And it is very, very similar, but it's not exactly the same, because what's going to happen is we essentially adjust for this off by 1. If I'm holding a stream, I'm always holding a suspension. Whereas with a lazy list, I would always have to be holding a value of the first element. Yeah. Like if I had taken away the stream and I had alpha lazy.t here, alpha front lazy.t. That would be equivalent to lazy list. It wouldn't be equivalent to streams. I need this guy here to make sure that I'm maximally lazy and I don't expose the first element. Oh, I see what you're saying. You're going to make this lazy. Yeah, that'll be fine as well. That'll be fine as well. Yeah. Yeah, that'll be fine as well. Yeah, you could do that as well, because as long as you don't do the work to do this until you really have to. Yeah. I think you could also, there's the thing when you get into like this kind of stuff, you start playing with type isomorphism. I'm pretty sure that would work. But there's like a bunch of different ways you could structure it. Yeah. If you don't quite see what he's saying, it's fine. This will be the canonical way that we do it. It is kind of interesting to think about different ways that we could formulate this. But that is the point of type isomorphisms, which you can take 312 to learn more about. Okay. All right. Okay. Does everyone see though? Like, I have another slide to explain this. Let me explain it first. Okay. So, conceptually, how I want you to think about a stream and a front. A stream is a delayed front. A front is an exposed stream. This might seem like a circular definition, and it is, but it's not circular in a way that's not useful. Okay. A stream is a data structure, a kind of lazy list where you have no license to look at the elements yet. There's a type level distinction between if I have a lazy list versus a lazy list where I'm permitted to look at the front. A stream is a lazy list, full stop. I'm not allowed to look at it. A front is a lazy list where I have license to look at the first element. To be able to look at something, I have to but I have to change the type from an alpha stream to an alpha front before I get reason to look at it. Okay, so we can be very, very clear with where our computations fall based on whether or not we have an alpha stream or if we have an alpha front. But if you have an alpha stream, no dice, you can't see anything. This is just a suspension, nothing to it. Okay, but if you have an alpha front, now we can play ball. Like now we can actually look at what's in the front. All right. Another way to put it is the only thing you can do with the stream is force it. But when you force it, you get a front where you have that intent to force. I alluded to earlier, you don't necessarily have the intent to force with the lazy list. The front is our reification, our that manifestation of intent to force. You have a question? Let's start with the stream. Stream will be the canonical thing. The point is that up front is like a degraded stream where we have expressed intent to force, but the stream comes first. Yeah. Okay. Yeah. Yeah, but that's a good question because we can start from anywhere. Yeah, and if we started from here, actually, I prefer we'd have the same issue. If we started with the front, we solved it off by one. Really, is what we did. Okay. Okay. Where I put the and. This one needs to be first. The second, if it has the and, at any rate. Like I could have done data type alpha front equals and alpha stream equals. Stream is first because conceptually stream is the first thing. Yeah. But it doesn't actually matter. Yeah. Okay. Okay, we're going to have our own signature for streams, and it's going to look like this. And I'm just going to tell you this part, which we already saw. But the point I'm making is that stream is an abstract type to users of the stream library, and this is the real stream library you will be using on your homework. You don't know what a stream is, and that's kind of problematic because now you need to be able to interact with the stream. You need to be able to make a stream. So let's expose some helper functions that will help us with that. Okay. But this is defined exactly the same way. We're going to have a structure stream that we're now talking about implementing that. Okay. So at the online 150 documentation, we're going to see this. You can see this structure, but it'll be implemented like so with the same type that I just showed you. Right. And then we're going to talk about what comes after. So first of all, I need a way to make a stream. We're going to call it. Actually, I think I give you the specs first. We're going to call it delay. It's going to have the same sort of vibe as a lazy.delay, right? If I have delay, I take in a unit to alpha function. Whoa, sorry. That should be alpha stream. My bad. You take in a unit to alpha stream, a suspension of an alpha stream, and you turn it into an alpha. Oh, no, I'm wrong. It's unit to alpha front. Sorry. Yeah. Basically, the point is that we should be able to define delay as such. This is the point. Okay. If I delay f, I just do that. Sorry. Yeah. Because I take in the unit to alpha front function and I just wrap it in stream. Delay is very uninteresting in terms of what it does. But the point is that this will let us do the type level hackery that we need. So units to alpha front quantity, and then promote that to an alpha stream. Okay, we promote a suspended alpha front into an alpha stream. And then expose takes the stream and then expresses that intent to force. And then we get an alpha front. So as soon as we do expose, we are now holding a value that tells us, yes, you have asked for the first element. This is like the ultimate case of parse don't validate. Like by holding an alpha front, you know that you force something. I cannot be holding an alpha front without having forced something. Okay. Or creating it manually. And so expose will be defined as such. If I have expose, I take in a stream, and stream is one constructor. So it's actually okay for me to do this. I just case on the one constructor here in this clause, and I don't have any other cases. And then I just say, let me use this f function of type unit to alpha front and get back an alpha front as a result. Does that type check to everyone? Very uninteresting functions. But the fact is that these two functions are going to be exposed in the stream signature, and it's how you interact with streams. And someone asked during the quiz about like why I should want to do delay and expose as opposed to like just using function application. This is very deliberate. If you wanted to find everywhere in a program where you exposed or delayed, you just control F for delay or expose. So it's very, very explicit in the program text what you're doing. All right. These are our functions. We will use them to define cool things now. Okay. But not that one. That one's done. All right. Everyone clear on this? All right. And that was the implementation, blah, blah, blah. All right. So we're going to use these helpers, and then we're going to define some cool functions. The first thing we're going to do is we're going to do the natural numbers. And the key to doing, I'm not going to have time to do the primes example. That's so sad. The key to doing the natural numbers is that what we're going to do is define two functions. One function operates on streams and outputs a stream. The other function operates on a front and outputs a front. Okay. Actually, for the next example, we don't need to do that, huh? We're going to do this. I'm going to show you through this. So here I have a function that gives back a stream and a function that gives back a front. I'll do the other example on the board. If I want to form an int stream starting from I, nats will be the one that's taking care of the stream. I delay a call to the front function. Okay. The front function is responsible for just coming up with a front. And it says, I want to have cons of I and then a stream where the stream is nats of I plus 1. You could also inline this. Okay, you could do fn unit goes to cons of I, nats I plus 1. That would be fine. But the reason why we do this is because particularly for some later functions, this will be helpful in terms of like making it conceptually very, very clear. One function gets a stream, one function gets a front. Okay? One type, one function, right? One function, one type. That's not true in the presence of polymorphism. Yeah, so we could have done it this way. All right. Do it however you like. I recommend this way. I find it useful. Okay. Let's do tabulate again, but let's do it for streams. Well, what we're going to do is something similar. So if I wanted to do tabulate but on a function, I would say f I, and this is going to be tabulate prime, actually, what we're going to find. And then this is going to be delay, the same stream.delay I told you about. I take in a suspension of an alpha front. So I say tabulate prime. Well, let's say this is prime, prime, okay? Tabulate prime prime given f and I, where tabulate prime prime is responsible with coming up with the front, okay? We could call them other things, but in practice in this class, what we do is we call it one, and then we call prime the other one. It's not necessarily great, okay? And what we're going to do is we're going to do cons of f given I, and then I need to come up with the stream. If you remember the type, the type's over here. That's so convenient. I need to come up with an alpha stream. So I call the original function again. So I call tabulate prime given f and then I plus 1. Note the circular idea, okay? Sorry, I need and, don't I? Yeah. I need and so I can define them so they are also mutually recursive, because what? Tabulate prime calls tabulate prime prime, then tabulate prime prime calls tabulate prime, okay? Mutual recursion, we just use and, okay? This is the same idea as, and then these helpers, then we just write tabulate where we start at 0, okay? Usually for these index-based things, we need a helper that takes in the index, okay? Everyone cool with this? Okay, we haven't used expose yet. Expose is usually used when we're writing a function on a stream, not a function that simply produces a stream. I want you to also understand why this tabulate is more lazy than the lazy tabulate we saw earlier. Okay, try it on the same example, see what happens. And some of you might get it now. But there's a reason why we did this, and that's because this tabulate is actually more lazy. Okay, all right. But like most data structures, what we can do is we can write a map function on streams. And you should be very familiar with this type signature, which is I take a map function, I take an alpha something, I return a beta something. Okay. Here's how we're going to do it. I'm going to have map, right? And I take an f and I take in a stream s. Here's where the divide becomes useful. I want one function to take in the stream, which is map, right? And output a stream, right? So let's write that function. Well, here's what I'm going to do. I'm going to delay, and then I'm going to make a suspension that simply takes the front of this stream and produces the corresponding beta front. I don't just want an alpha to alpha stream function. I want an alpha front to beta front function. Okay. Assuming we had such a function and it was called map prime, we're going to do this. Okay, and it'll make sense once I write the next function. Okay. Actually, let me write the skeleton. So map prime, and I'm running with very little chalk right now. This one takes in a front. So this one has two cases. Two cases. I get to case on the front now. So if I have the empty front, well, I can only give back the empty front, right? And then if I have, I need to write this whole thing out. F given cons of x, and then what do I have? I have a stream x comma s. I want to map this front. So what do? I just map the first element, right? And then I recurse, right? So for this stream, if I wanted to map this stream, I call map fs. And now we have to make the types work. Map prime takes in a front and gives back a front, right? So I have to give map prime a front, which s is not. So what do? Before I pass the stream to map prime, I expose the stream. Okay? It's a little subtle how this works, but here's how I want you to think, okay? First function is simply alpha stream and gives me back a beta stream. It does more stuff than that, but in intention, that's what it does, right? And then the second function takes in an alpha front and then gives us back a beta front, okay? What is a stream? A stream is a delay of a front. So we map the front, but first we have to expose it. And then when I deal with the front case, this is easy. I just do the empty and cons thing, but I have to map the stream. How do I map the stream? Oh, I happen to have a function which already maps streams. Okay. You can inline this, but I think this is a useful conceptual separation. I think this makes it a lot easier to write these functions. One function for streams, one reference. Yeah. Yeah. You know, I do the scoping in my head automatically. But yes, S prime would be fine as well. Yeah, fair enough. Any questions on this function? Maybe I will have time to get to the primes. Yeah. It's not an interesting case, really. Like, you can define a function of take, which takes the first n elements of the stream, and then you just do stuff on lists, pretty much. And this is a function which takes, right? Because look, what do we have to do? I had to look at each element of this stream in order to do that. So it's both. Where this is generation and destruction of the stream. Yeah. Is that a question? All right, cool. No worries. Okay. If everyone's cool with map, we will move on with gusto. And that's in fact what we have to do. But I'm going to caution you here because we could have done this in a pretty bad way. Okay. Here's the bad way we could have done this. I'm not going to write it all out, but here's how we could have done it. Okay. Okay. So we're back at map. This is a stream, and I want to produce a stream, right? So the first thing I do is I expose the stream, and if it's nil, I return the delay of nil, and if it's cons, I return the delay of the right thing, right? There's a big gaping problem we got here. What's our problem? What's the issue with this code? F of x? Oh, that one's fine. It has something to do with the thing about, here's the thing, right? If I'm mapping a stream, I have a stream which is like a delay of a lazy list that's maximally lazy. It means I have not expressed the intent to force. So why should mapping a stream cause an element to be exposed? Why should mapping a stream cause an element to be forced without me first saying I want to force it? The problem here is as soon as I call map, the first element of this function is exposed, which means that I try to expose this, but it might loop forever. It might raise an exception. It means that just mapping a stream is going to force the stream, which is not what I asked for. I want to be maximally lazy. I don't want to force. If I'm producing another stream on another stream, I should not force elements of the input stream until I have to. And until someone forces the mapped stream, that intent has not been displayed. Merely mapping is not the same thing as forcing. Okay? So what happens is I got too gung-ho about it. Do you see the difference here? With this function and that function, this function, I delay all this front nonsense I was going to do. So the front nonsense only happens if I expose and I get rid of this stuff. But here with map, automatically I expose, even if I didn't do an outer call to expose on the produced mapped stream. Okay. I have pretty much exactly the same sort of problem as tabulate, where I got too gusto and I looked at the first thing before I had license here. Do people see why this should be the case? And speak up now, please, if you don't. Okay, we'll move on from that. But yes, try running this code in your REPL and see what happens if the first element should be like looping forever, right? You'll see that mapping, merely mapping, is going to cause the first element to be exposed, and you'll loop forever, which is big bad. Okay, we don't like mapping. We don't like looping forever. Okay, so only in general when you're writing these functions, and your homework will make this very clear to you, but don't do stuff on the rest of the stream. Don't expose unless that expose is locked behind a delay. In general, okay? In general, it's not a good idea, especially if you're operating on a stream, okay? All of this stuff should be in thunk land because expose for expose. But here you get exposed either way, all right? So just be careful with that. The fact that it's not under a delay is the big problem here, right? We'll move on from that. I just wanted to talk about that. Blah, 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 blah. Okay, I told you already. And then let me also give you this definition, which is, you'll see on your homework, a productive stream is one where expose always terminates with empty or cons, where the S prime is again productive. Productive is just a keyword we use. It's a vocab word we use to mean a stream that has well-defined infinitely many elements. Or rather, not even infinitely, but it has well-defined elements, okay? It means that expose never loops forever. It never raises an exception, okay? That's all it means. It means that you can continuously expose and you will always get empty or cons. And that's all the intuition I need to give you for that. Okay. And generally we like productive streams because, again, we don't want to loop forever or raise an exception. But map has a curious thing where you could take in a productive stream and make a non-productive stream, right? Because what if this f raised an exception? So be careful with stuff like that. That's something to be wary of, okay? But also this will help us describe the specification of certain function, okay? For instance, we have the stream append function, where if append takes in 2 productive streams, it should produce a productive stream. So again, this append is exactly the same as our normal list append, but we're going to do it with streams. Do people see why productive will help us in this specification? Like if I get 2 productive streams, appending them should again produce a productive stream, yeah? Like one that has well-defined elements, yeah. What does productive mean? Productive is a word we use to describe streams. That is to say, like you can expose it continuously, and it will always give you emptier cons. Always, 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 and so on and so forth if you keep exposing. Basically, it will never loop forever to get the next element. It will never raise an exception to get the next element, which are possible scenarios. We want to avoid that, so we use productive to describe streams that don't do that. Yeah. Oh, yeah. Okay, cool. Sorry, I know I glazed over this kind of fast. I just really like the primes example. I want to get to it. I don't know. I'm selfish. I think it's cool. Okay, so okay. Well, I'll write it out. I'll write it out. So if I wanted to append 2 streams, same deal. All right, I'm going to have one function which operates on the stream and gives us back a stream. S1 and S2. Nub for nub. A little better. And then S2. And this is going to do the append thing. So first off, immediately what I do, I delay. I delay a call that does the thing on the front. But what do I delay? Let's wait on that for a second. Okay. And then I'm going to define append prime, which gets a front and produces a front. So in particular, I don't need to force both of these guys. I only need to look at the first stream I claimed to you to do this append thing. Kind of the same way how we only have to look at we only have to look at the left list, right? When we're appending, right? So same deal here. If I have empty, and just trust me that this is how we're going to do it. If I have empty here and I have S2, what stream is append the empty front in S2? S2, thank you. Indeed, that's correct. And then if I wanted to append prime, what's my next case? I'm going to do cons, right? And I have X and then S prime, let's say. S1 prime maybe even. And then I have S2 again, okay? Well, if I wanted to append this, I'm going to keep X on the front. And I have to produce a front, right? That's what this function does. Oh, sorry, whoops. Wait. I don't have a front. Ooh. Let's just do okay. Sorry. I have to make the types work out. I have to return a front here. If I return S2, I'm getting a stream. Sorry, my bad. In fact, I probably made the same typo on the slides. We'll see. Okay. Just trust me here. This one takes a front, gives back a front. Okay. And we're just going to keep, I'm just trying to make the types match. Okay. And then if I want to give back a front here, I say cons, and I keep the first element. But now I have to come up with a stream, right? Do I have a thing that can make a stream out of 2 streams? Oh, I do. Called append, right? Exactly. So I append the S1 prime, the tail of S1, and then S2. And then here I only have one thing I can do, which is that I have to make the types match. So I have to give it a front and a stream. So we're going to do append prime, where to get a front, I expose S1. And I'm going to run out of room here. But I'm going to put them on top of each other. As good, all good computer scientists too. Sorry if you can't see that. Yeah. There's a comma here. No, wow. Ooh, thank you. Thank you. Yes, indeed. So now yeah. Yeah, which is a good thing. Yeah, we never will access it until this thing is empty, which it never will be. That's fine. It just means that our append function will always carry around S2, but never force it if the first thing is infinite. Because what's the case where we force S2? Only when the first thing is empty. The by hypothesis you told me is infinite. it'll just always be carried around as a useless argument. The code doesn't know that's infinite. Yeah, so that's fine. Yeah. Yes, indeed. Yeah, it would be in the closure of the function. Yes, indeed. Yeah. Good observation. Okay. Is everyone clear on why this function should work? And if you have concerns about this expose being like maybe not maximally lazy, the reason why this is useful again is when we operate on a front, we already have been given permission to expose. So that means that if I'm fine to expose S2 because I was asked to expose the append of these two things. And if I can't do this, then I have to do this. No, I have no choice. So by doing this type level thing, I kind of am forced. I'm forced to do the right thing here. That's kind of why I like this. Yeah. Yeah, exactly. So like the second function, you have license to expose because you're inside thumb clamped. You have been given to get here. You had to have already exposed. Yes. Yeah. Append takes in two streams and gives back a stream. Append prime takes in a front and a stream and gives you a front. When I say front to front, I mean also with the stream in tow. Okay. But yes. Okay. Yeah, front and stream. Yeah. I was a little brief on that, but yeah, if you look at the constructors, this is the only interpretation that makes sense. Yes. And then this one gives us back a stream also, and this one gives us back a front. Okay. Did I give a specification? Oh, I did. Sorry, I should have. Well, append prime wasn't there. I should have written append prime too. But yes, thank you. Okay. All right, one more for the road. Filter. I'm not going to write this one out. I'm just going to tell you what it does. Okay. I want to filter a stream. Cool. All right. I'm not going to motivate this to you. We just want to do it. All right. This is how we do it. I want filter takes in a stream, returns a stream. I want filter prime takes in a front, returns a front. Same deal here. Okay. I should do expose here. Sorry. What's going to happen is I delay my call to filter prime, and in doing so, I have to expose S because filter prime takes in the front, right? And then filter prime, if it's empty, I can't filter the empty front. So I return empty. But if I have cons, I check if P of X is true. If P of X is true, I keep the X, right? So I do cons of X where I filter the rest of the stream. You could call this S prime if you wish. That might have helped, yeah. Otherwise, this is actually going to have to be an expose. I'm going to filter the rest of the stream and then get the first element of that. I have to make the types match. Okay. This is actually a useful thing, which is that like I'm lying to you here. This is not correct, but like this is a very clear kind of lying where if you plug this code in, it's not going to work. So like the best kind of lying is lying where you can check it mechanically. Okay. So I'm lying to you here, but what should be here is expose. Okay. The types will not work unless I expose S2 or the filtering of S2. I know that was brief, but this should feel the same sort of way. Okay. Where if I don't have anything, I have to come up with it eventually. So I expose, and also I maintain this duality of operations on streams and operations on fronts. Is everyone clear on that? Is everyone cool with this? Because I will talk through the sieve. I swear to God, I will. It's fine to ask questions also. It's important. Okay, cool. Okay, so one thing to note is map is interesting because map might give you a non-productive stream if you give it a non-total f. Right? If f loops forever, or if f raises an exception, you might get a stream that when you force the next element, it raises an exception or loops forever. That's what non-productive means, right? But filter might give you a non-productive stream even if you give it a total p. Suppose I gave a predicate function filter that was always false. If you expose the stream that you're working on, it will loop forever, assuming the input stream is infinite. Does that make sense for everyone? Because you're always going to look for something that satisfies false, which will never be the case. Yeah. Yes, exactly. Yeah, but it'll only happen when we get to that element. Yes, indeed. Yes. So this is also something I wanted to kind of just briefly mention. Kind of think it to yourself why you can get a non-productive stream from filtering with any predicate function, even a total one. Okay, this is kind of like good conceptual knowledge to have. Okay, all right. For 3 minutes, I want to talk your ears off about primes because I think this is super cool. Okay, some people will tell you the primes are infinite, and those people would be correct, but some people will tell you that. And in fact, that makes it a really cool application, a prime candidate, if you will, for talking about streams, because streams are also infinite. So let's try to make a stream that has all of the primes, okay? We're going to use something called the sieve of Eratosthenes, which tries to find prime numbers by excluding numbers which are not prime, okay? The idea behind the sieve is simply this, okay? As soon as I see it, so, okay. I am looking at all of the natural numbers. So I'm looking at these. I'm looking at all of the natural numbers that I know to not be 0 and 1 because I know that they're not prime, okay? But all of these guys, and the first one I look at, okay, well, 2, it must be prime, right? So I exit out, and then I exclude any element which is a multiple of 2. So gone is 4, gone is 6, gone is 8, gone is 10. And then I look at the next thing that satisfies. So I look at 3. Well, 3 now must be a prime because it's not a multiple of any previous prime. Sorry. I look at 2 and then I cross out its multiples. Yes, thank you. I look at 3 and then I cross out its multiples. So I double cross out 6 and then I cross out 9 and somehow we're done here. I cross out 12. And then I'm done. So this is a prime. I look at the next guy, that's 5, which is a prime. I cross out 15 and 20, right? You get the idea. So on and so forth. This is hard to do in a list because I can't have a list of all the natural numbers, but I could have a stream of 2 through infinity. I'm just going to talk you through this implementation right now, but here it is, okay? Divided by xy returns true if y is divisible by x, okay? So y mod x must be 0 for that to be true, right? Y is divisible by x. And then my sieve is going to take in a stream of natural numbers, s. I assume that that's the case. And then I just delay sieve prime on expose of s. This is just type level stuff, okay? That's not interesting. This case is going to be if I have empty, which will never happen if I have the infinite stream of natural numbers. And this is where the magic happens. If I get an element like 2 or like 3, I keep it. I know it's prime. But what I do is I filter out the rest of the natural numbers to not keep anything which is divisible by x. That's why I inverted the order here a bit. Like divided by is such that y is divisible by x, so that it would read nice when I partially applied it. But the point is that I filter the rest of the sequence, the rest of the stream to not keep this, not keep this, not keep anything divisible by 2. And the not there is to make sure that's not divisible by, right? And then I sieve that again. I continue to sieve on whatever the rest of this is to recursively ensure that our algorithm keeps going. And then I use tabulate to get all of the naturals from 2 onwards, and then I sieve that to get the primes. I think this is like freaking cool as heck. Like this is like 10 lines and I've given you all of the primes, okay? If your CEO walked into your office and was like, I want all the primes on my desk, this is how you do it. I'll leave this as a bonus to you to figure out why this works. I just wanted to briefly talk about it. Yeah. Numbers are not interesting, but streams are interesting. All right, cool. Okay, streams are fun, numbers are not. Thank you.